Hello, our project is Deep Q Learning for tree chopping in Craftium with reward shaping and visual augmentation. I'm Heijun.
I'm Ash.
And I'm Cheng.
So here's a brief introduction and background on our project. So in this project, we wanted to address the problem, which is how does reward shaping and visual augmentation affect an RL agent's ability to learn in a high-dimensional environment, such as Craftium? And so Craftium is an environment based on Minecraft, which is a first-person open-world sandbox voxel-based game. And we train a deep Q learning model in order to do a simple task in the game, which is to chop a tree. And we also modified the visual space by adding blur, crop, and edge mapping, which is meant to simulate the limitations of human vision. And in this presentation, will demonstrate what we've learned about reward shaping, our methodology behind it, and the success of our models.
So Minecraft is a pretty complex open world and partially observable 3D environment since the agent is from the perspective of first person and it can only see a snapshot of the environment at any given time. So this makes it a very highly complex state space and action space. Therefore, it's a pretty effective environment to test methods that are more similar to real life tasks. The task at hand we're doing is chopping trees, and the observation space is basically a 64 by 64 image with three color channels. And for this task, we have a limited set of eight discrete actions, four of which are just incremental changes to the mouse angle. So the to what constitute as chopping a tree is when a tree block is dug, and an episode is ran until a limited number of time steps. So the agent wants to dig as many blocks as possible during this time. Next. For this task, since the state space is so complicated, we want to parameterize the Q function. And this we do this by doing the deep Q learning method, which is inspired by the work by Min et al. In 2013, where they used deep Q learning to solve Atari games to achieve human level performance. So in short, algorithm basically selects an action with epsilon greedy policy, execute the action, and stores this transition in a replay. And then we compute the TD error and update the policy network. And every so often, we look in the memory replay, uh, sample a mini batch of transitions, and retrain this batch of transition. Next. So the visual augmentations that we will be doing are, you can see on the left, 75% edge blur, the middle, 75% center crop, and on the right, we use a canny edge detection algorithm to generate an edge map. And so our goal is to see if we could use these visual augmentations to significantly reduce the observation space while still retaining enough information so our agent can learn our task of chopping trees. Next.
And so here's our environment experimental setup. Our tech stack requires Python and Lua, and the RL framework is Craftium, which is built on Minetest. And the libraries you would need are PyTorch, NumPy, Gymnasium, and Matplotlib just for visualizing reward functions and seeing what's going on with the agent while training. And so our agent and environment is a DQN agent with a CNN-based Q network. And when we're training it, it's grayscale 64 by 64 pixel observations with discrete actions. As Cheng has said before, it's forward, dig, and then mouse actions. While we're training, we did 1,000 time steps per episode with 4 frames per frame stack with 4 frame skips. And so here's some details on the training and some of our reward shaping. So reward shaping ended up being a big part of our experience during this project because we realized that simply giving one reward, such as digging a block, was not enough because the rewards were so sparse. And so with our baseline model, we had a simple reward shaping functions. And for the baseline with complex reward shaping, we tried lots of different reward functions. And we decided for blur, crop, and edge map that we would stick with the simple reward shaping just because it was more robust and more predictable when we ran the final model. And so while training, we did 200 to 300 episodes, ending it sooner when we knew it was converging. And we had an epsilon decay from zero point 0.9 to 0.05 over 3,000 steps. And we did optimization with Atom, learning rate at 1 to -4 and at 128 batch size. And so the three simple reward functions we had was 15 for digging a tree block, -5 for digging a non-tree block, and plus 0.5 per time step of sustained digging. So we wanted to encourage that digging behavior. We had more other reward functions as well for the complex reward shaping, such as proximity and also punishment for looking away before finishing digging something. And here are some videos we'll play to show how it looks like when we're training our model. And here's another example. So as you can see, as we train our models, there are still some discrepancies between the end product, but we're still able to get the model to dig a tree block. And finally, this is one with edge mapping.
Okay, now let's talk about the results. So we plotted a couple of graphs, and some of the metrics we used were evaluation of reward per episode. For training loss, we used Q network loss over gradient update. And then the time steps that we measured was in episodes. So an episode would end over 1,000 time steps, as mentioned before. So the graph on the left here is using a complex reward shaping with our normal baseline model with no visual augmentation. And then on the right is a more simpler, or I guess in the middle is a more simpler reward shaping result. So as you can see here on the left with a complex reward shaping, the resulting graph is much smoother. But overall, both models basically start converging around 50 episodes. And then also with the training loss, you can see that the training loss decreases over time. Next slide. And then for these three graphs, these are the results of the visual augmentations that we did. So as mentioned before, we use simple reward shaping. And on the left here, we have the edge mapping result. In the middle, we have the reduced FOV. And then in the right, we have the blurred model. So from these results, we determined that reduced FOV and blurred helped converge the model much quicker. It helped the agent out with uh, properly defining a tree block and then digging it. And then, as you can see here in the edge mapping, it takes much longer to converge here. So it probably converged around 175 to 200 episodes. And overall, our experiment was very successful, but we were definitely limited by CPU usage and training time. And I think if we had more time or we had more resources, we would have been able to achieve much better results. So now let's talk about some of the things that we learned. So first of all, we learned how to integrate open source projects and external APIs with RL agents. Second, we learned how to implement a custom DQN with tailored reward shaping. And then third, we learned that visual alternation can stabilize learning in pixel-based environments. And then for our future direction, definitely want to be able to extend this framework to more complex problems and then more complex, I guess, environments inside of Craftium. So there's more things like being able to kill a spider or like craft a, a house or something. And um, also, we want to be able to develop more reward shaping strategies for multitask setups. So we definitely want to be able to generalize it to where it can not only mine a tree, but also know how to craft something and then do something else with that. And then the last thing is to definitely explore additional forms of visual degradation, such as being able to dynamically blur, and then also combining different visual alternations and seeing if that helps the performance of the agent. And yeah, that's our presentation. Thank you for listening.
Thank you.
You.